हेलो फ्रेंड्स, तो अकेडमी में आपका स्वागत है। हमने स्टार्ट किया 12th क्लास की एनसीईआरटी की वन शॉर्ट सीरीज, जिसमें हमने 7th यूनिट तक कंप्लीट किया है। तो हम स्टार्ट करते हैं 8th यूनिट, जो कि हमारा डी एंड एफ ब्लॉक एलिमेंट्स। द डी ब्लॉक ऑफ द पीरियोडिक टेबल कंटेन्स द एलिमेंट्स ऑफ द ग्रुप्स 3 to 12 to which the d orbitals are progressively filled to each of the four long periods. The F block consists of elements in which 4f and 5f orbitals are progressively filled. They are placed in a separate panel at the bottom of the periodic table. The names transition meters and inner transition meters are often used to refer to the elements of D and F blocks respectively. There are mainly four series of the transition meters: 3D series of S and Zn, and the 4D series Y and CD, 5D series L and HF and HG, and 6D series has AC and elements from RF, TS and CS. The two series of the inner transition meters are 4Y, 4F, CE2LU, and 5F, TS2LF are known as lanthanides and actinides respectively. Originally, the names transition meters was derived from the fact that their chemical properties were transitional between those of S and P or block elements. Now, according to IUPAC, transition meters are defined as meters which have an incomplete d subshell either in a neutral atom or in their ions zinc, cadmium, and mercury of group 12 having um, full the D10 configuration in their group ground state as well as in their common oxidation states, and hence are not regarded as transition meters. However, being the end members of the 3D, 4D, and 5D transition series, respectively, the chemistry is studied along with the chemistry of the transition meters. The presence of partly filled D and F orbitals in their atoms makes transition elements different from that of the non-transition elements. Hence, transition elements are and their compounds are studied separately. However, the useful theory of valence and as applicable and to the non-transition elements can be applied successfully to the transition elements also. Various previous precious metals such as silver, gold, and platinum, and industrially important metals like iron, copper, and titanium belong to the transition metals series. In this unit we shall first deal with the electronic configuration, occurrence, and general characteristics of transition elements, with special emphasis on the trends and the properties of the first law, 3D transition metals, along with the preparation and properties of some important compounds. This will be followed by a consideration of certain general aspects such as electronic configurations, oxidation states, and chemical reactivity of the inner transition metals. The transition elements D block. The D block occupies the large middle section of the periodic table and flanked between S and P block. On the periodic table, the d orbitals of the penultimate energy level of atoms receive electrons, giving rise to four rows of the transition metals, that is 3D, 4D, 5D, and 6D. All this series of transition elements are shown in table 8.1. Electronic configuration of the d block elements. In general, the electron configuration of outer orbitals of these elements in n-1 d1 to 16 ns 1 to 12 1 to 2, and the n-1 stands for the inner d orbitals, which may have 1 or 1 to 10 electrons, and outermost ns orbital may have 1 or 2 electrons. However, this generalization has several exceptions because of very little energy. The difference between -1d and ns orbital and more stable. The consequence of this factor is reflected on the electronic configuration of Cr and Cu in the 3D series. For example, consider the case of CR, which has 3D 5 4s1 configuration instead of 3D 6 4s2. The energy gap between the two sets 3D and 4s of orbitals is small enough to prevent the electron entering the 3D orbitals. Similarly, in case of Cu, the configurations of the outer orbitals of transition elements are given in table 8.1. Electron configuration of outer orbitals of the transition elements ground level. The electron configuration of outer orbitals of zinc, cadmium, Hg, and Cn are represented by the general formula Vn-1 d10 ns2. The orbitals in these elements are completely filled in the ground state as well as in their common oxidation states. Therefore, they are not regarded as transition elements. The d orbitals of the transition elements protrude to the periphery of an atom more than the other orbitals, that is S and P, as they are more influenced by the surroundings surroundings as well as the effect of the atoms or molecules surrounding them in some aspects. Answer of given d or configuration n is equal to 1 to 9 have similar magnetic and electronic properties with partly such as the display of a variety of oxidation states, formation of colored ions, and entering into complex formation with a variety of ligands. The transition metals and their compounds also exhibit catalytic property and paramagnetic behavior. All these characteristics have been discussed in detail later in this unit. There are greater similarities in the properties of the transition elements of a horizontal row in a contrast to the non-transition elements. However, some groups similarities also exist. All we shall first study the general characteristics and their trends in the horizontal rows, particularly 3D rows, and then consider some group similarities. General properties of the transition elements D block. We will discuss the properties of elements of first transition elements only in the following sections. Physical properties. Nearly all the transition elements display typical of metallic properties such as high tensile strength and ductility, malleability, high thermal and electrical conductivity, and metallic luster. With the exceptions of zinc, cadmium, Hg, and Mn, they have one or more typical metallic structures at normal temperatures. And the transition metals, with the exception of zinc, cadmium, and Hg, are very hard and have low volatility, and their melting and boiling points are high. Figure 8.1 depicts the melting points of transition metals belonging to 3D, 4D, and 5D series. The high melting points of these metals are attributed to the involvement of greater number of electrons from n-1d in transition to the ns electrons and the interatomic metallic bonding, and any row on the melting points of these metals rise to the maximum of at d5 except for metals rise to a maximum at d5 except for anomalous values of mn and tc, and fall regularly as atomic number increases. They have high enthalpies of atomization which are shown in figure 8.2. The maximum at about are shown in figure 8.2. The maximum at about the middle of each series indicate that one unpaired electron per d orbital in particularly favorable for strong and thermoatomic interaction. In general, greater the number of valence electrons, stronger is the resultant bonding, since the enthalpy of atomization now is an important factor in determining the standard electrode potential of a metal. Metals with very high enthalpy of atomization, that is very high boiling point, tend to be noble in their reactions. See later for electrode potentials. Another generalization that may be drawn from figure 8.2 is that the metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor in accounting for the occurrence of much more frequent metal bonding in compounds of the heavy transition metals. In general, ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. This is because the new electron enters of the orbital, which time the nuclear charge increases by unity. Now it may be recalled that the shielding effect of a d electron is not that effective. Hence, the net electron attraction between the nucleus and the outermost electron increases and the ionic radius decreases. And the same trend is observed in the atomic radii of a given series. However, the variation return within a series is quite small, and an interesting point emerges when atomic sizes of one series are compared with those of the corresponding elements in the other series. The curves in figure 8.3 show an increase from the first 4D or of the second 4D series are the first elements, but the radii of the third 5D series and the are virtually the same as those of the corresponding members of the second series. This phenomenon is associated with the intervention of the 4F orbitals, which must be filled before the 4D series of elements begin. The filling of 4F must be filled before the 5D series of elements begin. The filling of 4F before 5D orbitals, resulting in regular and decrease in atomic radii, called lanthanoid contraction, which essentially compensates for the expected increase in atomic size with increasing atomic number. The net result of the lanthanoid compaction is that the second and third D series exhibit similar radii, ZR 160 pm, JHF 159 pm, and have very high, small, similar physical and chemical properties of much more than that expected, and on the basis of visual family relationship. The factor responsible for the lanthanide contraction is somewhat similar to that observed in an ordinary transition series, and is attributed to similar cause, that is the imperfect shielding of one electron by another in the same set of orbitals. However, the shielding of one 4F electron by another is less than that of d electron by another, and as the nuclear charge increases along the series, now there is fairly regular decrease in the size of the entire 4F orbitals. The decrease in metallic radius coupled with increase in atomic mass results in a general increase in the density of these elements. Thus, from titanium to copper, the significant increase in the density may be noted. Table 8.2 electronic configuration and some other properties of the first series of transition elements. ionization enthalpy. There is an increase in ionization enthalpy along each series of the transition elements from left to right due to an increase in nuclear charge, which accompanies the filling of the inner d orbitals. Table 8.2 gives the values of the first three ionization enthalpies of the first series of transition elements. These values show that the successive enthalpies of these elements do not increase as steeply as in the case of non-transition elements. The variation of an ionization enthalpy along the series of transition elements in such a comparison of the variation of in general increase, but the magnitude of the increase in such a second and third ionization enthalpies for the successive elements is much higher along the series. The irregular trend in the first ionization enthalpy of the emitters of 3D series through of little chemical significance can be accounted for by considering that the removal of one electron alters the relative energies of 3s and 4s and 3d orbitals. You have learned that when d block elements form, ions less electrons are lost before n minus 1 d electrons. As we move along the period of 3D series, we see that the nuclear charge increase from scandium to zinc, but electrons are added to the orbital of inner subshell. Scandium and zinc but 3D orbitals. Their 3D electrons shield as 4s electrons from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another, and therefore the atomic radii decreases less rapidly. Thus, ionization enthalpies increase only as slightly along with the 3D series. The double D or more highly charged ions have of and along with the 3D series, the doubly are more highly charged ions of D configuration with a number of no 4s electrons. The general trend of increasing values of second ionization enthalpy is expected as the effective nuclear charge increases become 1d electron does not shield another electron from the influence of nuclear charge because the orbitals differ in direction. Enthalpy breaks for the formation of Mn dipositive plus F3 dipositive, not tripositive respectively in both the cases. Ions have D5 configuration. Similar breaks occur at the cases ions have a D5 configuration. Similar breaks occur at corresponding elements in the after a later transition series. The interpretation of variation in oxidation enthalpy for the electronic configuration Dn is as follows. The three terms responsible for the values of ionization enthalpy are attraction of each electron towards the nucleus, repulsion between the electrons, and the exchange energy. Exchange energy is responsible for the stabilization of energy states. Exchange energy is approximately proportional to the total number of possible pairs of parallel spins in the degenerate orbitals. When several electrons occupy a set of the degenerate set of possible extent of single occupation of orbital and parallel spins, hundreds rules. The loss of exchange energy increases the stability. As the stability increases and the ionization becomes more difficult, there is no loss of exchange energy at D6 configuration. Mn positive has 3D5 4s1 configuration and configuration of Cr positive plus D5. Therefore, ionization enthalpy of Mn positive is lower than Cr and positive. Cr positive in the same way, Fe positive and has D6 configuration and Mn positive has 3D6 configuration, hence ionization enthalpy of Fe positive is lower than the Mn positive. In other words, we can say that the third ionization enthalpy of Fe is lower than that of Mn. oxidation states. Table 8.3 oxidation states of the first law are row transition metals. Trends in M positive M standard electrode potential. Figure 8.4 observed and calculated values of or the standard electrode potential. Trends in M positive upon M positive standard electrode potentials. Trends in stability of higher oxidation states. Figure 8.4 the thermochemical data kilojoule per mole for the first row transition elements and the standard electrode potentials for the reduction of M positive and M2M. Table 8.5 formulas of halides of 3D metals. Table 8.6 oxides of 3D metals. Chemical reactivity of E6 values. Magnetic properties. Table 8.7 calculated and observed magnetic moments. Formation of colored ions. Formation of complex compounds. Catalytic properties. Formation of interstitial compounds. Alloy formation. Some important compounds of transition elements, oxides and oxoions of metals. The inner transition elements of block. Electronic configuration, atomic and ionic size. At 8.6 figure trends in ionic radii of lanthanoids. Oxidation states. 8.9 figure electronic configuration and ionic radii of lanthanum and lanthanoids. The general characteristics. The actinoids. Figure 8.10 some properties of actinium and actinoids. Electronic configuration, ionic size, oxidation states. Some applications of D and F block elements. Summary. D and F block summary. D and F block consisting of groups 3 to 12 occupies the large middle section of the periodic table. In these elements, the inner d orbitals are progressively filled. The F block is placed outside at the bottom of the periodic table, and in the elements of this block, 4f and 5f orbitals are progressively filled, corresponding to the filling of 3d, 4d, and 5d orbitals. Three series of transition elements are well recognized. All the transition elements exhibit typical metallic properties such as high tensile strength, ductility, malleability, thermal and electrical product conductivity, non-metallic character. Their melting and boiling points are high, which are attributed many of these properties. The maxima occur at about the middle of each series, which indicates so that one unpaired electrons per d orbitals is particularly a favorable configuration for strong interatomic interaction. along the series lanthanides contraction. This has four reaching consequences in the chemistry of the elements succeeding them. Lanthanum and all the lanthanides and are rather soft while white elements metals. They react readily easily with water to give solutions giving plus 3 ions. The principal oxidation states is plus 3, also plus 4 and plus 2 oxidation states are also exhibited by some. सो यहाँ पर हमारा डी एंड एफ ब्लॉक एलिमेंट्स का ख़त्म होता है. सो प्लीज़ इस वीडियो को ज़्यादा से ज़्यादा लाइक कीजिएगा एंड प्लीज़ सब्सक्राइब, लाइक शेयर एंड सब्सक्राइब. थैंक यू सो मच फॉर वॉचिंग. डी एंड एफ ब्लॉक एलिमेंट्स यहाँ पर ख़त्म होता है. थैंक्स फॉर वॉचिंग.